Hello, I am SP Basavraj, your host for this talk on optical fiber sensors. This talk is primarily meant for the physics stream students of VTU. The topic optical fiber sensors is in module 3 and comes under the title of optical fibers in the VTU engineering physics syllabus under the NEP scheme effective from the year 2021. Now to begin with, let's see what are sensors. A sensor is a device or a contrivance that is used to transform one physical variable into another, such that the resulting variation is proportional to the causative variation. The transformation is required in cases where the primary variation cannot be measured. After the sensor transforms the variation into another form, the resulting variation becomes suitable for measurement. Here we study two uses of optical fibers as sensors. The first one is about its use as a displacement sensor and the other one as a temperature sensor. Let's first consider the case of displacement sensor. A displacement sensor is a type of intensely modulated sensor. The principle on which it works is as follows. Here, the optical fiber is used as a sensor that converts the displacement of the object under investigation into a proportionate variation in the intensity of light. The working setup is as follows. The body in question is illuminated by a light source. When the body moves to a new position, its distance from the sensing fiber changes, altering the reflected light gathered by the fiber. The intensity of light is measured by using a photodetector. The change in intensity is proportional to the displacement of the body. That's the principle. Let's see about how the arrangement is done. Here you see a light source of high intensity. It's fixed firmly to a support. The support is not shown in the figure. This is the object whose displacement is under our investigation. This is an optical cable. It has a number of optical fibers neatly bundled together all along its length. This is its front end. It's fixed to an adjustable support. The light source is well behind the front end so that no light gets into the fiber directly. The other end of the cable, that's its back end, is also fixed to an adjustable support enabling proper orientation. The emergent light from this end is gathered by a photodetector and is measured as a corresponding electric current. That's about how it is constructed. Now let's see about how this setup works to sense the displacement of the object. The object is placed next to the cable. We name its position then as its reference position, say X. It is then illuminated by the light source. The orientation of the cable at its front end is adjusted till the photocurrent reading becomes maximum, at which inclination it is firmly clamped. The same procedure is repeated for its back end also. With this arrangement, let the reading of the photocurrent be Ix. That's the reading for the position X of the object. Next, the object is moved to occupy a different position Y. Due to the change in the distance, the intensity of light entering the cable changes. Let the corresponding photocurrent be Iy. Then the difference in photocurrent delta I equal to Ix difference Iy is proportional to delta L, the displacement of the object, given as delta L equal to X difference Y. Next is about the actual use. This arrangement can be used as a displacement sensor using the calibration graph, which is obtained as follows. It's simple. The value of delta I for different known distances delta L are measured, and then a graph of delta L versus delta I is made. That's the calibration graph. Now the object is released to follow its intended movement. As the object moves to different locations, its distance from the cable changes, resulting in different values for Iy. The actual displacement is then measured with the help of the calibration chart after evaluating delta I. Measurement of displacement following this procedure helps when the movement of the object is in difficult to reach locations. Through this method, the amplitude and frequency of vibration of a body can also be measured. That's about using optical fiber as a sensor for detecting displacement based on intensity modulation. Now we shall go to the next topic, that's about using optical fiber for measuring temperature on the basis of phase modulation. The principle on which the optical fiber works as a temperature sensor is as follows. An optical fiber elongates when its temperature is increased. Hence, the light travels a slightly longer distance in it, and accordingly it emerges with a different phase at the emerging end of the fiber. The difference in phase is proportional to the increase in length, which in turn is proportional to the temperature change. The change in phase is detected by a phase detector. Now, let's know what are the things present in the setup. It consists of a laser source to emit light, a beam splitter to divide the beam, a test fiber kept in the environment to be sensed, two lenses to funnel the light into the fibers. Now let's see how these are arranged. C is a chamber inside a whose temperature is needed to be measured. F1 is the test fiber and is spread inside C. F2 is the reference fiber of comparable length to F1. Here, interference is achieved by the technique of amplitude division. Light from a laser source is incident on a beam splitter. The beam splitter is a half-silvered mirror. It reflects a part of the incident beam while transmitting the rest. The plane of the beam splitter is oriented at an angle of 45 degrees to the direction of the incident beam. The transmitted beam from beam splitter is focused onto the receiving end of F1 through the lens L1. The beam emerging from its other end is reflected onto a phase detector by the help of a mirror. Again, starting from the laser source, the reflected part of the beam from the beam splitter is focused onto the receiving end of the reference fiber F2 through the lens L2. The emergent beam from F2 is also incident on the phase detector P. The phase detector measures the difference in phase between the two beams that enter into it. First, calibration is made by noting down the phase difference delta phi for different temperatures T inside the chamber C, and a graph of T versus delta phi is drawn. Then F1 is placed in the environment of unknown temperature and the corresponding phase difference in the phase detector is noted. Referring to the calibration graph, the corresponding temperature is identified. That's all about using optical fibers as displacement sensor and temperature sensor. For your reference, here is notes on displacement sensor and here for temperature sensor. Thanks for watching.